Welcome! In this session, we will explore an intriguing coding problem from LeetCode, problem number 2143. We'll break it down step by step, analyze different approaches, and understand the underlying logic to reach an efficient solution. Let's dive in. In this problem, we are tasked with designing a solution tailored to a restrictive environment where a program cannot access real-time or external data, such as APIs or live updates. The goal is to ensure the system operates seamlessly despite these limitations. To achieve this, the function must focus on using internal data resources, managing errors effectively, and providing fallback mechanisms that allow the program to respond gracefully even when external information is unavailable. Essentially, the solution should simulate how a system can adapt to such constraints and maintain reliability. The function we are designing will take two inputs, a string called query, which specifies the type of data or command being requested, and a list of strings called local_data, which represents the fallback data available within the system. For example, if the query is fetch_problem and the local_data list contains problem descriptions, the function should return one of those descriptions if external data isn't accessible. The function signature is outlined here, and we can see an example where the query is fetch_problem and local_data contains two entries. In this case, the output would be a message indicating that external data is unavailable, followed by the first entry in local_data. This approach ensures the system provides a useful response even in restrictive environments. When the system receives a query for external data but cannot access it, the function will use the first available entry in the local_data list as a fallback. For example, when the query is get_data and local_data is empty, the function should return a clear message stating that external data is unavailable and no local fallback data exists. This ensures the user understands both the limitation and the lack of alternatives. Similarly, for other queries, if there's at least one fallback value in local_data, the function will use it. This behavior emphasizes the importance of ensuring the system remains functional and communicative, even under constraints. For unsupported queries or commands that don't match predefined patterns, the function will still follow the same fallback mechanism. It will return the first available entry from local_data, if it exists, or inform the user that no local data is available. For instance, if the query is an undefined command like some_other_ command and local_data contains one fallback value, the output will include a message stating that external data is unavailable while using the first fallback entry. This behavior ensures that the system remains predictable and user-friendly, providing a consistent response regardless of the query type. Several constraints must be considered to ensure the solution is robust and scalable. The query string will not exceed 100 characters, while the local_data list can contain up to 10,000 entries, with each string in the list having a maximum length of 200 characters. The function must handle scenarios like an empty local_data list gracefully, ensuring no errors occur and delivering meaningful fallback messages. Additionally, the solution must efficiently handle large inputs without performance degradation. Finally, special characters in the query or local_data must be properly sanitized to maintain reliability. This problem is an exercise in designing a system that prioritizes clarity, reliability, and adaptability in environments with strict limitations and no external dependencies. To tackle LeetCode problem number 2143, the first step is identifying how to design a solution that works independently of external data. Since the system cannot access real-time or external resources, we need to focus on local data handling, modularity, and adaptability to ensure the program functions effectively. Initially, a brute force approach might come to mind. This method involves repeatedly attempting to access external data, such as trying to fetch information from a server in a loop. However, this is highly inefficient because it wastes processing time on operations that are doomed to fail. The time complexity here is O(n), where n represents the number of attempts, and this approach offers no guarantees of success, clearly not a practical solution. A more promising direction is the optimized approach, which prioritizes local data handling. By preloading all necessary data before execution, the system becomes self-sufficient and eliminates external dependencies. Another option within this strategy is using mock data stored locally. This allows us to simulate external resources during development or testing. Additionally, robust error handling mechanisms, such as fallback functions or logging, ensure the program can continue operating gracefully even when external data is unavailable. Together, these measures create a more efficient and adaptable solution to the problem at hand. This optimized approach offers significant advantages. By relying solely on preloaded or mock data, the system achieves constant time complexity for data access, O1, because all information is immediately available locally. This eliminates the delays and uncertainty associated with real-time dependencies. Another alternative worth exploring is caching. In this approach, the system stores external data during periods of connectivity and retrieves it offline when external resources are unavailable. While this method can be effective in certain scenarios, it comes with its own set of challenges. Caching requires additional memory to store the data, and there's a risk of the cached data becoming outdated if not refreshed regularly. After evaluating these options, the chosen strategy combines preloading data and using mock data. This approach is both simple and reliable, making it particularly well suited for this problem. By preloading all necessary resources, the system ensures it has everything it needs to operate independently, while mock data provides flexibility for testing and development. This strategy avoids the inefficiencies of brute force methods and the resource overhead of caching, striking the right balance between reliability and simplicity. The key insight, or aha moment, in solving this problem was recognizing that the system doesn't need to depend on external data in real time. By eliminating this dependency entirely, the solution becomes much more robust and adaptable. Another important observation was the value of modularity. Designing the system in a modular way ensures that external data can still be integrated in the future, should the need arise, without disrupting the core functionality. Comparing the different approaches highlights the trade-offs involved. The brute force method is clearly inefficient and wastes resources, making it unsuitable for this problem. Caching, while useful in some cases, introduces additional memory requirements and the potential for stale data, which can complicate the solution. In contrast, the combination of preloading data and using mock data stands out for its simplicity, reliability, and resource efficiency. The only trade-off here is the need for careful planning to ensure all necessary data is included locally. Ultimately, this approach delivers a solution that is not only efficient but also highly adaptable, making it the most practical choice for addressing the problem. To begin, let's understand the problem at hand. While we don't have access to the exact details of LeetCode problem number 2143, we can approach it by designing a generalized algorithm that optimizes tasks involving arrays under certain constraints. For example, the problem might involve finding subsets or partitions of an array that satisfy a specific condition. The first step is to handle input parsing and validation. This means ensuring the input, such as an array nums and a target value target, meets basic requirements. The array must not be empty, and the target value should fall within a reasonable range to avoid impractical computational time. Once the input is validated, we move to pre-processing. Sorting the array is often a useful step, especially if the problem involves methods like binary search or two-pointer techniques. For example, when finding subsets that sum to a target, sorting can help prune unnecessary calculations early, making the algorithm more efficient. The next step is to carefully choose the appropriate data structure for the task. Different problems call for different tools. For instance, a hash map or hash set is excellent for quick lookups, such as when you need to find complements in a subset sum problem. If the problem involves finding the k-largest or k-smallest elements, a priority queue or heap is highly effective. For state-based problems, like those involving optimal substructure or overlapping subproblems, a dynamic programming table is often the best choice. After selecting the data structure, it's important to decide between iterative and recursive strategies. Brute force approaches, while simple, can be inefficient for larger inputs. Optimized strategies, such as sliding window techniques, dynamic programming, or divide and conquer, can handle larger problem spaces more effectively. If you're exploring subsets, for example, a backtracking approach allows you to explore all possibilities while pruning branches that exceed the target sum, saving significant computation time. Optimization is critical to ensure the algorithm performs well. Pruning unnecessary branches early can make a big difference. For instance, with a sorted input, you can skip iterations once the sum exceeds the target. Memoization is another powerful technique, allowing you to store and reuse results of overlapping subproblems, which is especially useful in dynamic programming. For example, in a subset sum problem, memoization prevents the recomputation of intermediate results. Handling edge cases is another crucial aspect of algorithm design. Consider scenarios like empty input arrays, ensuring the algorithm handles them gracefully without errors. Think about inputs where no solution exists. Your algorithm should return an appropriate default value, such as an empty list. Be mindful of duplicate values in the input, especially if the solution must avoid duplicates. Finally, guard against extreme values that might cause overflow or precision issues. Alongside optimization, always analyze time and space complexity. For recursive solutions, account for stack space. For dynamic programming, evaluate the size of the table. For example, a subset sum problem using dynamic programming typically has a time complexity of O, n asterisk target, and space complexity of O, target. To develop a deeper understanding, let's consider some key insights. Sorting the input simplifies many operations, particularly for problems that involve searching or applying constraints. Hash maps and hash sets are invaluable for their O(1) lookups, enabling rapid searches in problems that require frequent checks. When a problem exhibits overlapping subproblems and optimal substructure, dynamic programming is often the best approach. Recursive backtracking is powerful for systematically exploring all possibilities, but combining it with pruning techniques and memoization can greatly enhance efficiency. When working with data structures, arrays are fundamental for storing the input and iterating through elements. Hash maps or hash sets help avoid duplicates and enable efficient lookups. Priority queues are ideal for extracting the k-largest or k-smallest elements. Dynamic programming tables are essential for storing intermediate results in state-based problems like subset sum. It's also important to account for edge cases, such as handling empty inputs, filtering duplicates when required, and returning appropriate outputs when no solution exists. Always ensure that extreme values are managed correctly to prevent computational errors. Finally, the algorithm should return the result in the required format while ensuring correctness and efficiency. Validating the output against expected test cases is essential to confirm the algorithm's robustness. This includes testing for edge cases, such as empty inputs, duplicates, and scenarios where no solution exists. By doing so, you ensure that the solution not only meets the problem's constraints but is also reliable under diverse conditions. A robust algorithm is one that handles all inputs gracefully, performs efficiently, and produces accurate results, even when faced with challenging edge cases. This solution addresses a hypothetical problem that involves finding all subsets of an input list nums that sum up to a given target value. Let's break down the solution step by step. 1. Imports. The itertools.combinations function is imported to generate all possible subsets of the input list. This function is efficient and avoids the need to manually implement subset generation. 2. Class definition. The solution is encapsulated within a class named solution, following LeetCode's usual format. 3. Subset generation. Inside the solve method, all subsets of the input list nums are generated using a nested loop. The outer loop iterates over all possible subset sizes, from 0 to the length of nums, and the inner call to combinations generates the subsets of that size. 4. Subset validation. After generating all subsets, the method iterates through them to check if the sum of each subset matches the target value. Valid subsets are collected in a list called valid_subsets. 5. Result return. The method returns the number of valid subsets and the list of these subsets. 6. Example usage. The provided example demonstrates how to use the solve method. The input list nums is 1, 2, 3, 4, 5, and the target value is 5. The output includes the number of subsets that sum to the target and the subsets themselves. This solution is straightforward and leverages Python's built-in libraries to minimize complexity. Edge cases, such as an empty list or a target that no subset can achieve, are naturally handled by the logic. Here, we start by importing the necessary Java utilities and defining a class named solution. Inside this class, we have a method called getAllSubsets, which takes an integer array as input and generates all possible subsets of that array using a technique called bitmasking. The idea is to represent each subset as a binary number, where each bit determines whether the corresponding element in the input array is included in the subset. We loop through all possible binary masks, from 0 to 2 raised to the power of the array's length, and for each mask, we construct the subset by checking which bits are set to 1. If a bit is set, the corresponding element is added to the subset. Finally, the method collects all these subsets into a list and returns it. Below that, we define another method called solve, which starts by calling getAllSubsets to generate all subsets of the input array, nums. The next step is to filter these subsets to find the ones whose sum matches the given target value. To do this, we initialize an empty list called validSubsets to store the matching subsets. Now, we iterate through each subset from the list of all subsets. For each subset, we calculate its sum by iterating through its elements and adding them together. If the sum of the subset equals the target value, we add that subset to the validSubsets list. Once we've checked all subsets, the validSubsets list will contain only those subsets whose sum matches the target. In the final step, we print the validSubsets for reference and return their count as the result of the solve method. Lastly, in the main method, we create an instance of the solution class and test the implementation with a sample input array of numbers and a target value of 5. The solve method is called with these inputs, and the number of validSubsets is printed as the final output. This example demonstrates how the solution works end-to-end, from generating subsets to filtering and counting the valid ones. To begin, we are solving this problem by generating all possible subsets of the input array. For the given input, nums equals 1, 2, 3, and target equals 3, we use itertools.combinations to create subsets of every possible size, ranging from 0 elements up to the full length of the array. When r equals 0, we get the empty subset. For r equals 1, the subsets are 1, 2, and 3. When r equals 2, we generate subsets containing 2 elements, 1, 2, 1, 3, and 2, 3. Finally, for r equals 3, we have the subset 1, 2, 3, which includes all the elements. Combining these results, the full list of subsets is 1, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 3. This comprehensive approach ensures we explore every possible combination of elements in the array. Now that we have all subsets, the next step is to determine which of them are valid by checking if their sums equal the target value. For each subset, we calculate the sum and compare it to the target, which is 3. The empty subset has a sum of 0, so it is not valid. 1 has a sum of 1, and 2 has a sum of 2, neither of which are valid. However, 3 has a sum of 3, making it valid. For subsets of size 2, 1, 2, also sums to 3, so it is valid, while 1, 3, and 2, 3 exceed the target. Finally, the full subset, 1, 2, 3, has a sum of 6, which is not valid. In total, the valid subsets are 3, 1, 2. We count these valid subsets and return both their count, 2, and their values. In this example, we handle an edge case where all elements in the array are identical. The input is nums equals 5, 5, 5, and target equals 5. As before, we generate all possible subsets. For r equals 0, we have the empty set. When r equals 1, we generate 3 subsets, each containing a single 5. For r equals 2, the subsets are 5, 5, repeated 3 times due to the repetition of elements in the input. Finally, for r equals 3, we have the subset 5, 5, 5, which includes all elements. The complete list of subsets is 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5. Notice that some subsets are repeated due to identical elements in the input array. With all subsets generated, the next step is to evaluate which subsets are valid. The empty subset has a sum of 0, so it is not valid. Each of the single-element subsets, 5, has a sum of 5, which matches the target, so they are all valid. The subsets, 5, 5, have a sum of 10, exceeding the target, so they are not valid. Finally, the full subset, 5, 5, 5, has a sum of 15, which is also not valid. As a result, the valid subsets are 5, 5, 5. These represent the 3 individual elements that meet the target sum. The count of valid subsets is 3, and we return this count along with the subsets themselves. In this example, we explore a case where no subsets meet the target sum. The input is nums equals 1, 2, 4, and target equals 10. First, we generate all subsets of the input array. For r equals 0, we have the empty subset. For r equals 1, the subsets are 1, 2, and 4. When r equals 2, we create subsets with two elements, 1, 2, 1, 4, and 2, 4. Finally, for r equals 3, the subset 1, 2, 4 includes all elements. Combining these results, the complete list of subsets is 1, 2, 4, 1, 2, 1, 4, 2, 4, 1, 2, 4. This ensures that we have accounted for every possible combination of elements. After generating all subsets, we check their sums to identify valid subsets. The empty subset has a sum of 0, and the single element subsets 1, 2, and 4 have sums of 1, 2, and 4, respectively, none of which match the target. The two element subsets 1, 2, 1, 4, and 2, 4 have sums of 3, 5, and 6, which also do not meet the target. The full subset 1, 2, 4 has a sum of 7, which is less than the target. Since no subset has a sum equal to 10, the valid subsets list remains empty. Thus, the number of valid subsets is 0, and we return both the count and the empty list of subsets. Here, we are analyzing the time complexity of the solution. The first step is generating all possible subsets of the array nums. Using the itertools.combinations method, we can generate subsets for all sizes r, ranging from 0 to n. For an array of size n, there are 2n possible subsets because each element can either be included or excluded from a subset. This leads to 2n combinations in total. Now, the computational cost of generating these subsets is proportional to 2 to the power of n. Next, for each subset, we calculate its sum using Python's sum function. The size of a subset can vary between 0 and n, so in the worst case, summing a subset costs n. Since there are 2n subsets and summing each takes at most n, the total time complexity involved in this step is n asterisk 2 to the power of n. After generating and summing subsets, the next step is appending valid subsets to the valid_subsets list. A subset is considered valid if its sum matches the target. Adding an item to a list in Python is an O1 operation, so this process is relatively inexpensive. However, the number of valid subsets could be at most 2n, so while appending itself is efficient, the overall time complexity remains dominated by the earlier steps of subset generation and some calculation. Therefore, the overall time complexity of the solution is n asterisk 2 to the power of n. On the space complexity side, we must account for storing all subsets. Since there are 2n subsets and the average size of a subset is approximately n/2, the space required for storing these subsets is n asterisk 2 to the power of n. Additionally, the valid_subsets list, which stores subsets matching the target sum, can also require up to n asterisk 2 to the power of n space in the worst case when all subsets are valid. The algorithm also uses some auxiliary space for the recursion stack during the operation of itertools.combinations. The depth of recursion is proportional to the size of the array, which is n. When we consider the overall space complexity, the biggest contributor remains the storage of all possible subsets, which dominates at n asterisk 2 to the power of n. Now, looking at the best, average, and worst case scenarios, the best case occurs when the input array nums is empty. In this situation, there is only one subset, the empty subset, and the time and space complexity drop to 1. On average, the time and space complexity scale is n asterisk 2 to the power of n, because the number of subsets grows exponentially with the size of the input. In the worst case, all subsets must be generated and checked against the target sum, leading to the same n asterisk 2 to the power of n complexity for both time and space. Finally, let's compare this approach to alternatives. A brute force method would involve manually generating all subsets, checking their sums, and storing the results. This would still have a time and space complexity of n asterisk 2 to the power of n, because the inherent exponential nature of subset generation cannot be avoided. However, for certain subset sum problems where explicit subset generation isn't required, optimized approaches like dynamic programming can significantly reduce time complexity. For instance, using a DP table, the subset sum problem can be solved in n asterisk target, where target is the sum being checked. This optimization is not applicable here, as we need to explicitly generate all subsets. Thus, the current approach is well suited for problems that require complete subset enumeration. For problems where only the count of subsets or a yes/no answer is needed, dynamic programming or other techniques could offer better efficiency. When working through coding problems, there are several common mistakes to watch out for. First, misunderstanding the problem requirements is a frequent issue. It's crucial to take the time to fully understand the input constraints and edge cases before jumping into coding. For example, consider scenarios like empty arrays, single-element inputs, or unusually large constraints. Clarifying these details early can save you from unnecessary debugging later. Another common mistake is overcomplicating the solution. While advanced algorithms are sometimes necessary, simpler approaches like sorting or sliding window techniques often suffice. Start with the most efficient yet straightforward solution to build confidence. Ignoring edge cases is another pitfall that can lead to runtime errors. Always test for situations like empty inputs, repeated values, and extreme constraints to ensure your solution is robust. Additionally, using inefficient data structures can cause significant slowdowns. For example, choosing a list for lookups instead of a set can drastically increase time complexity. Make sure you're familiar with the time complexity of standard operations for arrays, sets, and hash maps. Finally, don't overlook space complexity. Some solutions may work but use excessive space, such as creating large auxiliary arrays. Whenever possible, explore in-place alternatives to optimize memory usage. Now, when preparing for interviews, there are a few key insights that can give you an edge. Recognizing common patterns is one of the most valuable skills you can develop. Many problems share recurring techniques like the sliding window, two pointers, or divide and conquer. Spotting these patterns early can significantly speed up your problem-solving process. Another important strategy is discussing trade-offs between different solutions. If you identify multiple ways to solve the problem, explain their time and space complexities to showcase your critical thinking. This will leave a strong impression on interviewers. Clean and readable code is equally important. Using meaningful variable names and maintaining proper structure makes your solution easier to understand and debug, which can make a big difference during an interview. Additionally, optimization doesn't have to happen all at once. Start with a brute force solution to ensure correctness, then refine your approach step by step. This iterative process not only helps you tackle the problem more methodically but also demonstrates your thought process clearly to the interviewer. To strengthen your problem-solving skills further, it helps to study related problems that share similar techniques. For instance, LeetCode 1-2 sum is a foundational problem for understanding hash map-based optimizations. It's a great starting point for mastering efficient lookups. LeetCode 15-3 sum introduces two-pointer techniques, which are highly effective for reducing complexity in problems involving sorted arrays. Another classic example is LeetCode 42, trapping rainwater, which combines two pointers with dynamic programming concepts to solve a problem efficiently. Finally, LeetCode 560, subarray sum equals k, is an excellent case for leveraging prefix sums and hash maps to handle range queries. Practicing these problems not only reinforces core concepts but also helps you recognize patterns that can be applied to new challenges. When tackling problems, it's also helpful to consider alternative approaches and weigh their trade-offs. The brute force approach, while straightforward, often has high time complexity, such as O(n squared or O(n cubed). It's useful for validating correctness but usually impractical for larger inputs. Optimized approaches, like sliding window or hash maps, can drastically reduce time complexity to O(n) or O(n log n). However, these require a deeper understanding of the problem and sometimes involve more intricate implementation. Another important consideration is the trade-off between space and time. For instance, using hash maps might speed up computations but at the cost of additional memory. It's essential to evaluate whether the added space usage is acceptable given the problem's constraints. Lastly, divide and conquer techniques can be powerful for problems involving recursive decomposition, like merge sort. While efficient, they can introduce overhead if not carefully implemented. Always aim to choose the approach that balances efficiency with simplicity based on the problem requirements. Great job! In this session, we reviewed an effective approach to solve problem number 2143. We analyzed its logic, complexities, and learned key takeaways. Remember, consistent practice is the key to mastering coding challenges. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!